conocido a...
estamos aquí los dos, Rafa.
Siéntate aquí, Rafa, venga.
Pues mira, ya está, pagamos nuestra estancia.
Operadores.
Dime, ¿qué tenemos que hacer?
Nada, cambiar de primer plano, porque esto tiene dos rollos, que es primer plano y plano general. Y entonces Claro,
bueno, hay
tío.
algunos huequitos
Entonces, el primer
todavía.
plano es la cámara reflex esa que está ahí, que si la quieres cambiar, tú te dedicas a cambiar rollo. Se supone que el sonido está entrando, pero es lo que no tengo comprobado. Espero que esté
¿Y
saliendo
entonces qué
bien.
tengo que hacer?
Nada, cambiar de primer plano a general cuando te dé la gana.
Sí, ya está.
Sí, sobre todo
ya
si
está
quieres-
grabando incluso, o sea, ya
Sí,
está.
ya está emitiendo.
¿Ya está emitiendo y ya está todo?
Sí, ya está.
Ah, vale,
es lo
vale.
que estaba intentando comprobar, porque está emitiendo aquí en el canal mío. Sí, mira, estamos ahí.
Ah, pues de puta madre, pues yo me quedo aquí de operador.
Te quedas de operador y
Ya
haces
está, ¿ves?
esos dos rollos. Mira,
Gracias,
perfecto.
Eso lo vigilamos.
Joder, perfecto, tío, porque es que ya. Y es que,
No, pues me toman nosotros y me voy a quedar fuera.
pues esos dos rollos y nada más, no tiene más historia. Luego, si quieres enfocar la cámara,
Nah, no, mejor no toco.
es fácil. Ahora, como está el plano general, tú puedes tocar aquí, ¿sabes? Hacer el rollo, enfocas al colega o pones las transparencias, lo que tú quieras. Este enfoca solo, debería. Debería enfocar solo. Le das aquí medio flash para que enfoque solo.
Pero Vicente, aquí no se está reflejando eso que estás
porque
haciendo.
Pues primer plano.
Porque está en plano general. Cuando pones plano.
Ah, vale.
¿Qué mierda es esto? Estos
plano-
ratones raros. ¡Ah!
Sí, gusta aquel. Te lía. Vale. ¿Ves? Entonces yo siempre juego pongo el plano general, me dedico jugando a la cámara y cuando me gusta, ya, como que. Esto es un OBS con dos logos y dos chorradas.
Sí, bueno, pero está bien.
Esas son mis cosas de la época de la pandemia.
Ah, yo pensé que ahora la sacaba vicerrector ahora. ¿Cuánto lo hago de todos los días vicerrector?
Ahí ya. Pero bueno, capaz.
Bien, bien, bien.
Mira, estoy viendo la discusión de la red de la planta tercera.
Sí,
Está la cosa.
Preguntarle a los chicos, ¿qué sabes qué pasa? Que los cables son muy blancos, hay una misterio de paquete por la longitud del cableado.
Pero es ahora, ¿no? Antes no estaba pasando tanto.
lleva meses, o sea, ya lleva, no sé si meses o de siempre, no te sé decir, pero...
Es que lo curioso es que no pasó eso de repente.
Ah, ves, entonces...
Lo curioso es que le pasa en unos despachos sí y en otros no.
A ver, hay despachos que no han dicho, hay algunos que por el perfil yo diría que esto no hace mucho piso. Y eso es un rollo de streaming.
Claro, por
un
la
rollo de streaming.
latencia en los cables largos, hay que pierde la calidad, que baja el rollo. ¿Por qué? Porque
Aunque bueno, Belén sí debería. Por eso debería...
no consigue siempre, la olla está más cerca. Porque puede ser 10 metros de diferencia.
Claro.
Y se le fastidia, porque está en el borde de la distancia certificable. Claro, los switches están en el centro del patio. Nosotros estamos en la otra punta.
Pero no había un armario en el mismo módulo A.
No lo sé.
Había uno, hay un armario en el módulo A. Sí, abajo, ¿no?
A mí me dijeron que no, es que el cableado está bien.
Los creía que había un armario allí, ¿crees?
Entonces, lo que tú encendías cuando se iba la luz, ahí había algo de red, o solo era luz.
Ahí no hay nada de red. Pasan los cables.
Ah, yo pensaba que era un armario de comunicación allí. Ya, pues claro, ahí está...
No sirve, yo sé. Eso da esos problemillas. Bueno, pues si te tengo ahí de...
Sí, ya me encargo, te
Voy a poner el plano general. Eso es, desenrocas un poco para que la muevas y luego la vuelves a apretar. Ok, ya está. Lo que no sé es si se está oyendo algo, si no se está oyendo nada, porque el audio no me dio tiempo de probar. Voy a salir un poquito fuera.
¡Oh, pues de puta madre!
Sácate unos samples.
No, cara no, que tengo que currar para... Tengo que pagarme el sitio, ¿eh? O sea que... Pero bueno, ya está. Bueno, Rafa, tú mueves, tú eres el operador de cámara y yo... Voy a dar un primer plano un momentito ahí de los tres que están... Ah, sí, un rato.
Y dale al zoom. ¿Oíste? Hazle al zoom.
No, está... Ahí están los ponentes. Está en streaming.
Está en streaming. Seguramente luego se grabe.
El audio estuvo como micrófono.
El audio fue comprobar lo que se. Yo creo que si está ahí es que lo está oyendo.
No hay ni cobertura, tío, de la...
No hay. Yo te dije que. Así salió.
Estas son las llaves del coche de Vicente. Ay, mi madre, Vicente.
En el palco 20 años, esta vez...
No, me trancó Vicente y no tenía sitio yo ya, digo, pues te echo un cable con esto, pero nos sentamos.
¿Eso están transmitiendo por streaming?
¿Sí?
Ah, pues mira, para uno de por streaming.
Está aquí en el canal de Vicente, creo que. El YouTube de Vicente. Bueno, no hay mucha cobertura, pero. Era el propio canal de él, ¿no? Porque el canal personal. Creo que es el canal de Vicente.
Bueno, estamos aquí para un poco disfrutar, porque yo creo que todos aquí vamos a disfrutar de una charla del profesor Stroustrup. Para los que no lo saben, muchos de los que tenemos una cierta edad estudiamos todos los libros del profesor Stroustrup. Quizás mi primer contacto con C++ fue que le damos un compilador y te lo digo para entender cómo funciona la vida. Ya hace unos cuantos años. La verdad que es un verdadero placer tener al profesor Stroustrup en nuestra universidad y bueno, ver que sigue activo, que sigue trabajando en las explicaciones de C++ y que bueno, nos va a poner el foco en cómo será los recopiladores de lenguaje C++ y los compiladores para este lenguaje de cara a los próximos años. Todo lo que esté en esta sala que programe videojuegos no le va a quedar más en el medio. Va a aprender a programar muy bien en C++. Y me consta que en esta escuela se trabaja y se enseña con mucho
Si quieres mover uno, va todo. Enfócalo ahí. Y si que se vea la presentación y ahora lo voy a cambiar.
Since I was here together with Bjarne,
Muévelo.
met earlier, and said, let me give a talk.
Subir un poco la ganancia porque
And
se
so
veía un poquito casi a lo
we're
mejor, no sé si
going to
ahora
get
pasé.
this. And it's not specifically written for me. Maybe there's some bits that doesn't fit, maybe there's some bits that can't get around to, but there is a written version of this. I have the slides available, there's a paper available, so you can follow up on the bits that I get across.
Está muy oscuro detrás.
So
No sé si
basically,
se puede
this
montar de alguna
talk
forma.
was written because I was a bit fed up with people writing C++ as if it was the 1980s. I mean, we can do much better.
Abre un poquito más si
And
quieres.
that's what I'm trying to explain to you. What is it in this millennium and what the previous one? So basically, you can do just about anything in C++. And that's an opportunity and it's a problem because people choose the wrong things sometimes. If you can do anything, you have to choose what it is you want to do right. So have an analogy, Goto can do anything. That's why we don't use it. We want to have things that are better behaved, easier to use, easier to check, da 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 da. So it's not easy because we carry with us our past in the heads and in the old textbooks and in the old programs. So I'm trying to
to help you get over the hump and write modern C++. So you'll see on my slides there's sometimes some pictures. So there's one there. It's one of the very early video games. A lot of the video games are C++ these days. This one is specific, it's special because it's done by Douglas Adams. If you know the Hitchhiker's Guide to the Galaxy and such, that's what it is. And you'll find that there people are using computers a lot. I did not know that they were using C++ till I met one of the people that did the game with Douglas Adams. So the pictures have something to do with C++. I'm not going to explain them all. So here's an example of a modern C++ program. First, we grab the whole standard library, importing it. Then we say, I'm going to use the standard library's namespace. And then we go in, main, of course, and I want a string of a map of string and integers. Because what I'm going to do is I'm going to do this awk program. That's the one that outputs every unique line in a file, or in an input in general. And people use it for logs and things like that. So basically, for all the input, read a line. Once you've read a line, stick it into the map and increase the count by 1. If we started out with 0, it's a new line, and so we print it. So this prints every unique line in a file. Okay. There are people who talk that C++ you have to use new all the time, you have to do error checking, The point here is all of this is implicit. There's no explicit allocations. This will work as long as your unique lines can fit in the memory. No sizes, no error handling, no type conversions, no pointers, no preprocessor use. Some of you may have heard I don't like the preprocessor. That's an understatement. It's a source of many of the problems in C and C++. And it's quite efficient. And like everything else in C++, if the design is all right, you can tune it. I'll proceed to do so, because if you look at this program, it's probably not the fastest way of doing what it did. But if you only do it once or a few times, this is a nice little program. So I wanted to have a different version. Usually we don't just write a program, we write a function or a class or something that we can use again for something else. So here I am collecting lines from input, and I'm not saying anything about uniqueness, but I'm just taking a string. And then I read everything in, insert it into the set, and that gives you the unique lines. And unordered means it's a hash table, so it's efficient. And here I'm going to take the set and turn it into a vector, because once you have collected things, you usually want to do things with them, and vector is the most useful data structure for things you, in general, want to do things to. But you don't know what it is you want to do in the future. And so there, collect the lines and write out all the lines. Since it was a set, these are now unique. And if you are interested in performance, you will find that this is still not quite efficient enough. There's some copying going on. We'll deal with that later. What did I want with C++? What do I want with C++? There's a list of things here. The first one, most important, is I want to be able to say things clearly and directly. I don't want to fiddle around with the details and show how all the implementation is. I want to say, do this, where this is what I want done. I like static type safety. It's absolutely essential. I got it from Singular. I noticed the mention of Preston Igor. It's important. Resource safety, I don't like leaks. I mean, resource leaks, memory leaks, log leaks, file handle leaks. If you're writing code for, say, a spaceship, you do not want to leak. If you want to write things for just about anything, you don't want leaks. Direct access to hardware, one of the strengths of C++ throughout is that if you need to do things to hardware, even unusual or dangerous things to hardware, you can. Just don't do it all the time. I want performance. I want C++ to be faster than just about anything else. And part of this then comes, how do you manage performance while you also manage the complexity? That is, you don't spend all your time messing with the hardware at the low level, so what you don't use, you don't pay for, so zero overhead use, and you want to extend things to new levels of abstraction to make things easier. I want it to be affordable. Concurrency support, I don't have time to talk about concurrency today. There's one slide apologizing for that, but that's all. Otherwise, I could spend the whole day. Maintainability, platform independence, aka portability, and stability. There's people who wrote programs in the previous millennium that are still running, and you probably still depend on them. They may be on your telephone, they may be in your camera. So we don't want to break that. On the other hand, we want to write things better, easier, safer than what we could do back then. And the reason for being so keen on stability is that the fact that 10 and 20-year-old programs can run today is about the only guarantee you have that the programs you write today will run 10 and 20 years. And then contemporary C++ is not just to use all the new features. If you go to YouTube, endless people telling you how the latest and greatest should be used all the time. And that all the old stuff is bad. This is not true. C++ has evolved over the years, and along the lines, it has gotten rather nice things that we use today and are a basis of what we have today. And the new stuff is not all there is to it. So there's basic things, classes with constructors and destructors, that's the real start of C++, exceptions, templates, and then there's new modern things that you can use. But don't get drunk on the new features. See what features are what you need to solve your problem. And don't grab everything. What matters is to use the features as a coherent whole. And well, this is why we're here, this is why we're talking. There's a lot of use of C++ has been over the years. I go on the web and some people say C++ is useless. Well, if you say that, you're saying the people that wrote those programs were idiots. That's not a good idea. They were not idiots, they are not idiots, we can do really good things. And I'm not going to go into language wars, because one of my principles is I don't say anything bad about C++ applications, and there are interesting C++ applications here. Okay, so I'll focus on 4 things here, because I'm going to try and finish in an hour. We'll see if I can do that. But basically, resource management, including control of lifetime and error handling, because if you can't control lifetime, you will find that error handling becomes very difficult. Modules, because finally I've got modules, I don't have to use all of those header files. Generic programming, because it's a key thing and something I've worked on for years. And then I'm going to try and look at how to guide and enforce use of better styles of C++. Because, again, we need help. Otherwise, we fall back onto doing things the old way, which is not always good enough. And well, there's a book in a few languages. So resource management. A resource is anything that we have to acquire and then give back again to release. I mean, ask any librarian. Everybody takes out books and they forget to put them back. And so this is not a computer science problem, but it's a problem we have to solve. No leaks. And so we would like things to come back implicitly, not relying on people to remember to give a file handle back or some memory back or a book back to the library. And so examples, memory strings, logs, find handles, sockets, thread handles, transactions, shaders, and graphic system. All of these are things you acquire and give back. And we avoid the resource leaks by, well, basically making it implicit, guaranteed. And we do that by representing resources with a handle and having the handle have a scope. When you go out of scope, things get cleaned up. That's the idea. So here is the simplest example of a C++ program that I'm going to show. Basically, we have a vector. It's a vector of t's, where t is the element type. And what it does, it lifts from the low-level, machine level of representation pointer with a size to something that is constructed properly and destroyed at the end. So when we now use a vector, we have a vector of doubles, and some well-known constants here, vector of strings, of some hopefully well-known designers, and more complicated stuff here, more computer sciencey stuff, a vector of pairs of strings and J threads. Basically, I'm making a pipeline, concurrent pipeline. The point here being that everything is cleaned up right there. The constructors make things, and implicitly the destructor is called that cleans up the mess. So this happens recursively. So when VP, that vector, gets destroyed, it first destroys the pair first destroys the strings, the J thread destroys the J thread, the J thread releases the memory and the operating system resources just grab there. And this, by the way, is the real start of C++, and the real root of C++ came in the first or the second week I was working on this, because I came out of an operating system and machine architecture world, and I really wanted to control my resources. This doesn't just make sure you don't leak them, it actually makes it very likely that you release your resources as quickly as possible. If you wait for a long time, like with a garbage collector, then you are holding resources for longer. And there's been some measurements showing that if you do equivalent programs in C++ and C#, C# holds the resources for twice as long on average. But that means you need twice a bigger computer, because you're not reusing your processor and your memory and your file handlers and such. So anyway, this is good stuff. So control of lifetime, we construct, we destruct, we copy, and we move. Copy, of course, is a standard thing in computing. You make a copy of something. But you know, a lot of times when we copy things, we then destroy the original. I mean, only a computer scientist would get a handle over here by making a copy and then destroying the original, right? I mean, even 6-month-old babies can see it moved over here. It's now here, it's not here. So that's what the move is about. You can move it. So let's go back to the to collecting lines again. All of this is okay. Then I make the vector here and I return it. Notice I'm returning a vector of strings. There may be a million strings here. That could be expensive if I copy it, so I don't want to copy. I want to move. I want to move that res there. And the way we do that is we make the result res, and then we want to get it into lines. And so basically we steal the representation, put it into lines, and remove it from res. So we have now passed two strings, or maybe a million strings, but the maximum cost evolved is 6 word copies. As a matter of fact, we can do better than that. We can figure out that this res is coming out here and actually allocate res out here. That's what I've been doing since '83. So the maximum cost of that apparent copy is 6 word copies, which is fairly cheap on a modern computer, and the average is 0. I was talking about zero abstraction cost. Here's an example. Okay, let's rewrite it a little bit again. Connect the strings, and there's a constructor for sets that says do it from a range. That means treating the iString iterator as a range, so it reads range from the beginning of input to the end of input, and then I move the set that I got there into the vector, again telling it was a range. I would have liked not to say from range, but the standards committee decided that that was too subtle, and now you have to say from range if that's what you do. And then I can just say auto lines is correct the lines. That's not bad. It's been running close to optimal. The copy out of here has been done. I was panicked for a couple of days in '83 when I couldn't do that move. Then I did it, and now the standard guarantees it. So that's fine. But there's an important detail. If you look there, it says it reads into a line. The standard library doesn't have a line. It has a string, and a string reads white space separated words. In other words, it does the wrong thing. So I say line, it doesn't exist. Then I'll just have to make one. Perfectly ordinary, old-fashioned programming. A line is a string that you happen to read with getLine. So here we're falling back to code the way we were writing it back in the 80s. And that is what makes the modern code elegant. We don't just get drunk on modern features. We use features as they are appropriate. Okay, fine. So there's one more thing. Well, here, I'm moving the strings in that set into the. I'm copying the strings from that set into the vector. I don't want to copy it. I mean, I don't need them again afterwards. So I want to move them. And the compilers are not clever enough to figure that out. So we can tell it. Please don't copy, move. So what we have here is the first version is really simple. Anybody can write it after about 10 minutes of teaching, or maybe an hour. This stuff is a bit more subtle, but the point is you can tune things. You can take something that is good, elegant, clean, as long as it has enough information to do things. Optimizers and people can improve it. And so you go down and you improve the code. There also I wanted to write out again the unique lines for all lines in the result of collect lines, write them out. Again, I don't see any allocations, I don't see any loop indexes, and it runs really fast. There is enough information for the optimizer to do a good job of this stuff. And by the way, one of my rules of thumb these days is if I want to optimize, the first thing I do is to throw away all the clever stuff and see if it actually helped. Quite often, the clever stuff is complicated, it confuses me, and it confuses the optimizers. So write it simple, measure, and then improve if you need to, and only if you need to. Measure, that's the important word here. So tuning, it's essential for some code. I mean, the digital signal processing in your phone and computers and such, you really need to be optimal. But don't optimize prematurely. Create interfaces that allows you to optimize if you need to, measure, and then do it. So basically what you can do is you can manage complexity. You write something elegant at the top level. If that's good enough, it's good enough. If it isn't, you peel off a layer and mess with the details. If that's not good enough, you peel off a layer again. And you peel, and sometimes you may actually come down all the way to specialized hardware. But you know, each time you peel off a layer, you cry a bit. There's more work, more opportunities to make mistakes. This is why I refer to this as the onion principle. Okay, so anyway, make things tunable, make things elegant, and then tune when you have to. Resources and errors, in general, you don't read, but you know, you don't leak and you don't leave an object in an invalid state. That's the basic rule for error recovery if you have to. So when an error happens, before accessing the function that found the error, put every object access into a valid state and release every object that a function owns. So valid state is the same as having invariance. It's the basis of thinking about errors and correctness. I'm not going to go into that, but when you create a class, the constructor establishes an invariant, and the destructor cleans up any mess that might be there at the point of destruction. And here's an example of some code. I have a gadget G, and I have a gadget that I got with new. I see a lot of code like this these days because there's languages that really want to say new all the time. This comes out of Sigurd via Java to C#. So when people want to have a user-defined type, they knew it and put it over on the free store. I decided I didn't like that. I wanted my types, the ones I write, the user-defined types, to behave like the types that Dennis Ritchie had invented, like int. And so here I have a local variable gadget. Here I have a not so local variable, a new gadget, which I point to. And this is asking for trouble. Look, if I get out of here, what happens to that pointer? It leaks. If I have a return statement, it leaks. That's no good. By the way, the gadget, the destructor will fire there, there, and there. No problem. So basically, don't use explicit new in application code. New and delete belongs in resource handlers in code written specifically to handle resources. If you see this in sort of general purpose code, it's a code smell. It indicates that maybe you have an overhead you shouldn't have. This one is more expensive than that one, by the way. There's an extra allocation. And whenever you have a new, you need a delete. And you might have forgotten it. So try not to do that. So basically, for error handling, one of the important things is actually to think about error handling and articulate what you mean. How are errors handled in your program? A lot of people like error codes and tests, in which case try to make sure that you actually test consistently. People don't. When did you last check the output of printf to see if the output really happened? No, you didn't, and I didn't either. We forget. But you know, in systems with networks and complicated stuff, sometimes output simply doesn't happen. So once in a billion, you get a really bad mistake by not testing the output of printf. And printf is a very simple example. So basically, if you're using error codes, be sure you do testing. Otherwise, use exceptions for failures that are rare. That's why it's called exceptional, and cannot be handled locally. Things that propagate up the core chain to somewhere that knows how to handle it. And in particular, you handle errors in constructors, operators, functions that don't have an easy way of returning an error indicator. And by the way, returning an error indicator as part of your return value quite often doubles the size of your return value, and you have a cost of memory. And then you have to test it, and you have a cost at runtime. Exceptions doesn't suffer that. There's a new paper, which I reference at the end, that shows you can actually run significantly faster in smaller programs with exceptions. I'm just trying to deal with some superstition back from starting back in the 90s that exceptions were extraordinarily expensive. In some important applications, unconditional immediate termination is not an option. It's an option in some programs. So for instance, your Chrome browser quite reasonably kills your tab if something bad happens. That's fine, your browser is still running, you just open a new tab. As one of my friends says, I used to program oxygen controllers for scuba divers. There's only one processor. Don't terminate. That's pretty dramatic. I haven't seen that myself, but I've seen financial systems that under legal obligations, if they crash, they must crash in the middle of a transaction. It may be your money that's disappearing. So you're not allowed to. In some applications, there are a lot of people today that says, just terminate. Well, at least I want log and terminate, log and reinitialize, or something like that. This one is worth it. Okay, so error handling. There is a list to the efficient use of exception paper. It's a talk from, it's on YouTube, it's from CPPCon last year. And here is a piece of code, sort of archetypal kind of code, but squeezed into a single slide. Try and write that code and make sure you test for every error. It would fill several slides, and most likely we wouldn't catch every error because we don't know what comes out of the lower levels of the system. Here's a simple example. I'm simply putting Dennis's middle name in. There's a lot of ways of getting that wrong. Okay, so now to something really new. It's deployed in all major compilers these days. It's not equally good everywhere. It's actually best over at Microsoft because of my friends my friends Gabriel+Reyes working there. But basically, let's look at things. In the old ways, include A, include B. If you do it the other way around, well, you might get a different answer because there can be dependencies. And include is textual inclusion. This This implies that include is transitive. Means that if I include a header file and you include my header file, I did that, you get what I included. Whether you want to or not, whether you understand what you're doing or not, you're going to get it. And you get a lot of it. And that gives much repeated compilation because the compiler has to compile this stuff again over and over again because it might have changed. And there's some subtle bugs that happens. Modularity is what we can get now. Import A, import B is the same as import B, import A. This allows the compilers to work much, much better. Import is not transitive. If I'm using something, it doesn't mean that you, my user, get this, can also use it. That's not what it meant. Much compilation can be done once only. So here's an example. I'm making a module called a map printer, one I found that I could fit on the slide. I import IOStream, I import containers. This is my container library, which you don't have any interest in. Using namespace std, you know you don't do that in a header file, but this is not transitive. This is something I use and you won't see if you're my user. What you're seeing here as my user is I export a print map function that takes a sequence of elements and goes through the sequence of elements, breaking them down into key value pairs and outputting them. But the important thing here is that this stuff is isolated from you completely, and it's really easy. You just say import map printer and you can now map print. Okay, this has important effect on performance. Here's an example that a user did a couple of years ago. They are doing a library for device management and graphics. And so you include that library and you get close to 500,000 elements once everything has been expanded. That's 150,000 non-blank lines, and it takes a second and a half to compile. You know, compilers are really quite efficient these days. You give it 500,000 lines, it takes a second and a half. That's not bad, but it's not good either. Especially not if you include that one 100 files. Now you get 100 times that. Now with import, there's 5 lines for the compiler to look at, 4 blank lines, and it takes 64 milliseconds to compile. That's rather better. That's a 25 times compile time speed up. So we've actually managed to get old code to compile 25 times faster. This is interesting to do for an old language. We can still do it. We've done it. Watch the video here where she explains it. It's really dynamite. It's worth watching. Your head will spin. Mine did. She is using all the new fancy features and using them well. That is definitely an advanced course. Oops. No. That's definitely an advanced course. Anyway, I did a little experiment myself. I said include Hello World or import the whole of the standard library for the Hello World program. And you know, I got 10 times more information available at a tenth of the time. So there's a factor of 100. You don't get that all the time, but my impression is that you think about between 5 and 10 times speed up, and maybe 7. Think in that ballpark. Okay, and there's a reference there. Now I'm going to talk a little bit about generic programming, because well, that's central to C++, and it's central to what wasn't in C and what wasn't in Singular, and something that's been in C++ from the beginning. I used to do it with macros, didn't work too well, but with It's always there. It basically gives shorter, more readable code, more direct expression of ideas, zero overhead, and it's time safe. That's all good stuff, and it's absolutely basic in the standard library. All the standard facilities are generic in some way. So basically, what I can do is I can have a generic function. Sort works for any sortable range. I'll explain what that is in a second. And so I can take a vector and it checks whether the vector hits a sortable range. A sortable range is defined as something with random access where you can compare elements. Yeah, I can do that for a vector of strings. I can do it for an array of fixed size integers. Still, it works. So basically, here I specify what sortable means, and then becomes implicit what the type of container is, what the type of element is, the number of element comparison data. There is a lot of stuff we don't have to remember because the compiler already knows. And it checks right there that the information needed is available. We can try also with a list of integers, and it'll refuse. Because a standard library list does not have random access, and doing a sort on something that is a list that doesn't have random access is very, very slow. If you want to sort a list, do something else, like copy it into a vector, sort it, copy it back again. Anyway, so the C++ support for generic programming is based on 3 aims. It has to be extremely general and flexible. I used to go around saying it must be able to do much more than I can imagine. I know my limitations. A room full of people like this can have many more good ideas than I can. Zero overhead, you have to be able to afford to do this generality. I was in France where they were telling me that anything you abstract is slow. No, I don't like that. I want abstraction that I can afford. I want zero overhead abstraction. And I want well-specified interfaces. We'll get to that. Here's a skeleton of a simple traditional generic sort function. Give me a random access a type that's a random access iterator, default comparison criteria to sort. Give me 2 iterators to the beginning of the end and compare it with a predicate. This is the way we have been doing standard library functions since Alex Stefanov introduced them in the early 90s. Okay, so I can now do things. I just said that. Here is an array, and here's a vector of strings. I can begin end of the sort of the vector. I can sort the array. I can sort half of the vector. I can do the vector with a comparison criteria that's different. I do greater as opposed to less than, which is the default, and I can do begin end of the array, and I can put in a lambda. A lambda is an expression that generates a function object, which is a function that can have state, but operates like a function. We've had those since 83, but the notation here is relatively new, so only 14 years old, and there's still people who think it's new. But anyway, you can do this. This is flexible, very efficient. So this style, very general, flexible, traditional now, since we've been using it since the 90s, since a lot of you were born. But it's not type checked until late. This implies atrocious error messages, really awful error messages. We couldn't do better. Close to optimally efficient and very successful. I mean, I think there's more generic code in C++ than there are in all the languages that came before, and the criticism from the Java crowd and the C# crowd for about 5 years, were very loud, very vicious, and then they copied the ideas. However, the interfaces violate something fundamental. Interfaces should be precisely specified and hold enough information to check either compile time or runtime. This is violated by that old style. So we had to do something about it. So we did. We figured out how to do it. We was primarily me and Gabby Reyes, and the Sutton also helped a lot. Anyway, so let's look at concept. Concept is a compile time predicate, and we're going to use them as a predicate for template arguments. Are you a random access iterator? Are you a comparison function? I mean, basically, simple question, yes or no, and so we need a predicate. And we need it executed on types and compile time. So that's what we do. So here is the definition of what a sort of a range is. A type R is a sort of a range if it is a random access range and it has a sort of array. That's what the standard says. You look it up in the standard. You don't have to write this from scratch. That's what it is. So now what I said on the previous slides is true. It's not quite general enough because I simplified it. We need to have a predicate also, and we need to default the predicate to this, because that's what the standard has said for almost 30 years, so you better get it right. Sort of a range is a random access range, yeah, and it's sortable using that predicate. Fine. It is not enough to be able to say something in sort of an academic paper in 2-column format. It actually has to be flexible enough to be used for a wide range of applications out in the wild. And the standard library algorithms are very general, often with many parameters and overloads, so I don't recommend you read them in great detail now. Look at them when you need it and use them in the simplest possible way that is good enough for you. You'll see what I thought was good enough for me most of the time. It's something simply used here. So here, what we got, here's what the sort will look like. It has a sort of a range, and it has, the sort of, with a predicate, the predicate is defined to be defaulted to less. The syntax is, well, it's syntax, we get used to it. So the vector, we sort it with a different criteria, that's fine. We have a list, we try to sort it, and right there we get a decent error message. It says that list isn't a sortable range, and maybe it will explain to you that it isn't a sortable range because it doesn't have random access. And we can also build concepts from scratch. Here is equality comparable. It requires that if you take a T and a U, you have to be able to compare them with equals and with not equals, and you have a Boolean as a result. Again, you need a new syntax to be able to say new things. This is a very, very general way of manipulating types. Don't expect that to be explained in one page. It close to is, but how to use it is more complicated. And by the way, we can use static assert, another one facility. Are int and double equality comparable? Of course they are. How about equality comparable int? So if you just use int, you have a homogeneous system. Yeah, it just defaults the second type to the first, so that's also true. And I can try not equality comparable in string. Yeah, that will succeed too. Actually, if I took away the not, it would be fail, and the program wouldn't compile. These things here gates the compilation. You can't pass one of those if it fails. And so concepts, usually concepts have more than one parameter, because our templates usually have more than one parameter type. And if a function takes more than one type, there should be a relation between those types. They're not totally independent. If they were, what were they doing in the same function? And so I find that about half of all of my concepts have two arguments. This means that we are not talking about types of types. We really are talking about compile time functions, predicates, running. Yeah. Am I running out of time? Thank you. I don't have a time tonight. So we've always had concepts. I mean, Dennis had concepts in C++ 79. You just look. Arithmetic and floating, it says so. In English, we're just teaching the compiler to understand it. It also, in the process, becomes more precise and becomes checkable by a compiler. We are formalizing the notion of a concept. And the name concept was invented by Alex Stefanov way back. And STL has iterators, sequences, containers. Math has monoid, maths, groups, rings, fields in group theory, and graphs have edges and vectors. Basically, every generic program has concepts, if nothing else, in the designer's head, otherwise they wouldn't work. And so we have to use the language support efficiently. And basically, this is a sub-branch of compile-time programming. A lot of stuff in C++ these days is done at compile time. Const expert, stick that in front of the function, and it says it must, if it is given constant expressions, it will be evaluated at compile time. Const eval says it must be given constant expressions so that we get computed at compile time. And of course, there's concepts that also take types. And basically, they have interesting properties. They can't have side effects, they can't access non-local data, they can't have undefined behavior. It can use just about every thing that is well behaved. So this is C++'s version of pure functions, and you can use it today. It's been around for a while. Capitalist Race and I introduced them back in 2010 or thereabouts. Okay, compile-time programming, there's an example. It saves us from writing macro hackery. It saves us from writing error handlers, because the compiler is now our error handler. If there's an error, it will not pass. And here's a little example. It's actually a real example, into the square root. I had a request from a Japanese embedded systems manufacturer. They wanted this one here, so I built it. And into the square root of 1, 2, 3, 4. If the compiler couldn't do it for you, you'd have to do it on a doodle pad or something. And then you could get it wrong, and since some of the things we calculate a lot happens to be dependent on machine properties, they can become wrong over time. So it's good that we have the check here and get it right. And it works for user-defined types too. One of the rules of C++ is that we would like the same rules for user-defined types and built-in types. And so here we can have is last year's Christmas a Tuesday, and the answer is yes. If it isn't, there's a problem. Types and concepts are not types and types. And yes, Lego uses C++. Concepts, benefits, supports good design. It's another level of support of design and for explicit expression of ideas. It started with classes, now we can do it with templates and concepts. It gives better error messages, gives better overloading. And so I just want to remind you, there's still people living in a world where they don't have built-in types and no classes at C. They at least use the modern syntax and argument type checking as I added to C, but still I would not like to live in that world, and I would also not like to live in a world where I couldn't use concepts for exactly the same reason. So here's an apology slide. I can't talk about concurrency. I just don't have time. It is used all over the place for efficiency and threads, blocks, sharing, parallel algorithms, cooperative cancellation features, coroutines. All of this is available. You can read out on it. There's books on it and such. Okay, so how do we try? What is the best we can do to try not to get stuck in the 20th century? And basically, we get major benefit if we can use the language appropriately, and if we don't, we can write old-style code and get old-style problems. Upgrading code is really, really hard. For nothing else, there's billions of lines of stuff, and there's millions of programmers, and they're all busy. They don't have time to learn new things. At least they think so. But how? So, the first thing we do is code guidelines. We can't change the language. As I said, millions of lines of programmers. Millions of programmers, probably about 7 million. Billions of lines of code, definitely dozens of billions of lines. That's not something that's easy to upgrade, and nobody likes upgrading old code because that's messy and ugly. It's much nicer to write new stuff. So what we need is guidelines, individual rules that can be used or not. Guidelines is just guidelines. People don't have to follow them. That is a problem, but it's available now. Together with friends and colleagues, I did something called the C++ core guidelines. There's a link at the end. Otherwise, go to GitHub and type in core guidelines, you'll find it. What you need is enforcement. And that is called profiles. Basically, the idea is we show people how to do things better, and then you can ask to be caught at compile time if you don't obey that. It's being worked on in the standards committee and elsewhere. It is not available yet. Well, there's a little bit of it available in the static analyzer for Visual Studio and in Clang Tidy, but not as much as I would like. So let's see what we're going to do. Simple subsetting doesn't work. People have been asking for roughly day one of C++, can't I get something that subsets the language so I don't have to deal with the things I don't like. The problem is the things that people don't like are the dangerous, complicated things that you need to implement. Higher level, easier to use, more elegant features efficiently. So we need a standard library which is implemented with all of these ugly old things. So the idea is extend the language with a few abstractions, the STL, a tiny library, the guideline support library. So basically you extend it like this, and once you've extended it, you can say, well, don't use new and delete except in resource handlers, which will give you some of. Don't use pointer arithmetic except when you are doing your special memory management or your special container thing. So you can say don't use there. Now you can cut fairly simply. This is the subset of superset philosophy. I wrote a paper about that once. Basically, what we want is C++ on steroids. Something that's simple, safe, flexible and fast, and not some kind of subset where you can't say things, or where you can't say things efficiently, or where you have to do runtime checking of everything. So what we're working on is basically the core rules, the core of the core, and no uninitialized variables, no range and null pointer variations. This, by the way, is obviously a runtime check, no leaks if we use the constructor destructor stuff, sometimes called RCI. We can avoid that. No dangling pointers, that's harder. I'm going to show you a little bit about that, I think. No type violations through pointers, no invalidation. I mean, this can be done. If you go for my well, there's some links at the end about this. This is a whole world of checking how to do this right. Here's the example. Don't subscript pointers. There you just cut every existing C program. However, we have alternatives. We have vectors, we have spans, we have lists. You don't actually need to use pointers all the time. So here's the common style, pointer, comma, size, and then you can try and subscript. If you have an array, you can call it with that. This will work. Of course, depending that n meant the right thing. Was n the index of the last element, or was it the size? I have seen those bugs. But anyway, this is usually okay. Here we are asking for trouble. And usually that number is not a number that you can see like 100 or 1,000. It's a value I that you got from somewhere. Here is a huge number of the security violations, the safety violations of C and C++. So we want to make it simpler, shorter, and at least as fast. And the way you do it is you have type that we got out of the guideline support library and got into the standard. And here we take array. Give me a span of over A, and that's the function. And here we have f of A. It just says here, that should not be A, that's a bug. Imagine that this should, imagine that A is there. I'll fix it before it's probably. Here, f of A, the compiler extracts the pointer and the size of the array and sticks it into the span, and now you can manipulate the result with full knowledge about the number of elements. And here you have to actually use a slightly more complicated syntax to make the mistake. So it's easier to catch doing reviews, things like that, or static analysis. This one has a smell to it, this one doesn't. The simpler one is the one that doesn't smell. So that's a good thing. Here is a thing that's very important to deal with, and is not done very well except a few places. So here we have a vector, and we do a pushback. This is good. The effect is that the vector will grow with one element. That may mean that it gets reallocated. So here, I'm doing something bad. I have a vector with two elements. I take a pointer to the beginning, to the first element. Now I call this function, which, since it adds an element to it, will probably reallocate the elements so that there's room for that 9 I'm putting in. And then I use this pointer again, which may point into nothing. We can do static analysis to catch that. And I wish it was done systematically. I know how to do it. We have implementations. The Standards Committee has not agreed with it. There are proposals, but they're not there yet. So here are my suggested list of profiles, things that you should be able to ask for in your code. Please check these things. All ranges, noted DRMs in, arithmetic, catch your underflow, da 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 da. None of this will make C++ 26. I spent a lot of time trying to get into 26, but the committee was, in my opinion, too conservative, and didn't quite believe the problems were as bad as people said, and didn't quite believe they could do it in time. There's work going on. My guess is that by the end of the year, we will be able to get a fair amount of this. And hardening libraries, which deals with the subscripting in the standard library, is being shipped by Google and Apple. So some of this is happening. So if I sound a bit grumpy, it's because it's not going as fast as I like. It's not that it's not going. Okay, so, and the idea is we explicitly express it. It's not something that's imposed over all C++ programs. Either you get checking or you don't. Either you get guarantees or you don't. No, that doesn't work, not at scale. You have to be able to say, I start here, this is critical, I'm willing to modify my code for this critical stuff to get these kind of benefits. So that's what we need. So basically, here's the C++ model summed up. We have a static type system with equal support for built-in types of user-defined type. I really didn't want different scope rules and access rules for, say, integers and complex numbers. Complex numbers are a library type, not a built-in type. And value and reference semantics, because value semantics is really nice. You saw it with vector. But you need to implement it. And for that you need pointers, you need the reference semantics. Systematic and general resource management. We need object-oriented programming, we need generic programming. We need a lot of stuff done at compile time because, well, that means we get smaller memories, we get less runtime stuff, slightly longer compile times, but actually this isn't anywhere near as significant as the cost of template metaprogramming or other old-fashioned techniques. Concurrency support coming through libraries. I've been saying this one many times as fashions changed and different support for concurrency came in. If I had built concurrency into C++, as I was told many times that was the one right thing to do, it would have been outdated. And this would have happened repeatedly. Eliminate the preprocessor. I really don't like it. I don't use it anymore, except for when I have to use other people's programs. We have replacements for everything now. Okay, so the value of the programming language is the quality of its applications. That's my philosophy. That's what I go for. That's what motivates me. I look at what people do, and if they do it, then that's good. If they don't do it, at least we can see it, we can try and improve it. So there's some applications, and you know, it sort of worked. It grew over the years as it was expected to. The user population grew and is still growing. So that's how it is. And here's a bunch of references that you can follow on, because nobody should expect to understand something like C++ after tomorrow. And yeah, thank you. as I said, I do not have a time device, I do not know what time it is.
We have time for a couple of questions. Any questions?
Thanks for your contribution to the work with C++ and for the talk. I have two questions. What will you take to a person to convince them to use C++ instead of modern languages like C or Rust besides the overly used C++ in the world?
I would say something like this talk or the paper that covers some of this. C++ is a modern language, and it is more, and it is more flexible and more general and more available than the other languages. If you want to write code for, say, a power supply, then you can do it in C++. I met a guy, I was pretty surprised, I didn't even know there was a processor in there. A real one that you could write code for. It's not just writing nice little programs for browsers and such. It's wider use. And also, it is in many areas a better language. If you like generic programming, most of the alternative languages are not as flexible and efficient at that. And then, of course, the so-called safe languages tend to call unsafe languages and unsafe code. So do it. The unsafe language that they want to call is usually C++, written as if it was C. So they're not actually solving the problem, they are outsourcing it. And well, C++ can't outsource it. We can sort of outsource it to the old style of C++, but that's as far as we go. There's no other language for doing that.
And my other question is, what do you think about memory arenas? So you have a pointer to a linearly alloc memory, a cap that is the size of the memory, and you have a cursor that you iterate and points to the free chunk of memory. And when you are done with that, you deallocate it. So what do you think?
First of all, you should use an allocation mechanism that has an implicit deallocation, the constructor-destructor stuff like vector. And when you iterate over elements, either all of them or a subset of it, you should use something like span that can range check. The standard library range check was vandalized, so it isn't guaranteed. Use the GSL span, which does proper range checking.
Okay, thanks.
Any other question, please?
Hello, hi, I'm Bjarne. I have two questions. One question, basically two questions. Regarding models, are they fully compatible with technology libraries? And so, how difficult will it be to migrate other libraries to use to be a model-based one?
I don't understand the questions. My view of model-based is basically the view coming from Singular, that having a design with a strong static type system and a good set of types. And that is what the C++ is. And so either I totally misunderstood the question, or this was my answer.
Any other question?
person that is studying the college, would you recommend studying the latest version of C++, let's say 23? Or do you think it's better to start from something a little bit older, like C++ 14 or even older?
No, I think you should always use the latest compiler. It has the best error checking and the best code generation. So always use the latest implementation. It could be Clang, GCC, Visual Studio. I usually use Visual Studio for symbol checking, and usually GCC for deployment. But yeah, it's a nice thing to do. At which level of language? Now, to learn C++ well, I really think you need to read a book. You need a coherent view of the language. And YouTube and the web in general does not have a coherent view. So, read a book. The problem is that the two best books I know are mine. So, it feels a bit wrong to say, but I must. You can check on places like Amazon. You'll see I'm not the only one of this opinion. If you are already a programmer, get the book called A Tour of C++. That one, 3rd edition. And that will walk you through relatively modern C++, and it will ignore a lot of C++ that I either think are too clever or too old-fashioned. It has another virtue. It's 250 pages. There are people who can read it in a weekend. But do the exercises also, then you can't do it in a weekend. If you don't know how to program, if you've never seen C++ before, you should use a book that I have put on this list called Programming Principles and Practice Using C++. They both use basically C++ 20 with a few touches of C++ 23. In particular, they include import STD. You can also use them by the usual import, but I really like that import. So I will have to remember all of those names of the header files and such. But do something reasonably modern, like C++ 20. Don't go overboard with the absolute latest, which are always heavily advertised by people. And they are not always implemented quite as good as they should be, and they are not always available on all the compilers. Whatever I teach runs on all compilers. And sometimes they are over-enthusiastic. In the PVP book, it's the Programming Principles and Practice Using C++. Pointer was introduced in chapter 17, together with you. You can get a long way without going there. What I really do is I use things like strings and vectors, and then I say, okay, now let's take the lid off and see how it works. And then I use vector implementation as a quite sophisticated introduction to pointers and explicit memory management. You have to know it sooner or later, if nothing else because lots of people write it. But it is better to learn without getting into trouble for the basics, and then learn later how to get lower, closer to the machine, getting into trouble. At least by then you'll have an idea of how to get out of trouble.
Okay, one last question more there. Last question.
So this question has me really intrigued because when you were about to design C++, you were using Simula, you were using COBOL, and whatever it was called, I think it was Pascal, and you wanted something that were good enough for production, but still had a better type system than the other languages at the time. Or correct me if I'm wrong on this, but what I want to know is, did you at the time consider doing C++ as a superset of C, like actual spy language that turned something that is more than C into C, or something else than just writing a fully fledged compiled language?
Oh dear, lots of questions.
We can leave it.
Yeah, I'll answer. So, actually, every good language starts with a problem. And my problem was that I decided that I was at Bell Labs and there was all of these really smart, accomplished people, so I really had to do something good and interesting, otherwise I didn't belong. And so I decided I was going to build what would have become the first Unix cluster. I was going to build a distributed Unix. And for that, after some quick analysis, I realized that I needed two things. I needed to be able to manipulate hardware very well. The device drivers, memory managers, process schedulers, that kind of stuff. And C was a really nice language for that, for the time. On the other hand, I needed to abstract from that. I had to be able to say, here is some kind of module in the operating system, and it talks to that module over there, and they may or may not be on the same machine, so they can't share memory. If they share memory, that has to be hidden under an inter-process communication mechanism, In other words, I needed hardware access, optimal efficiency, and I needed abstraction that I could afford to use in that context. And that's the real origin of C++. Simula gave a good start for the abstraction mechanisms, and C was available. I mean, Dennis Ritchie and Brian Kernighan was down the corridor, so the support was superb. And so that's where it came from. And I tried to be a little bit more incompatible with C in the first few weeks, months. That didn't work. My colleagues advised strongly that I shouldn't do that. And in the end, I only did one major, massive incompatibility, which was I insisted on function argument type definition, declaration and checking. And for 10 years, everybody who didn't like C++ complained about that. And then C adopted it. So if you've written C, you've been using syntax designed by me with semantics mostly designed by me. Whenever you call a function. And const was also mine, by the way. The inline, anyway. So that's C today. Did I answer all of your questions? Thank you.
Thank you very much, Professor. It's been a pleasure for us, a great opportunity, an honor, and thank you very much.
Thank you very much.
hace que no lo utilices a menos que sea muy largo, ¿sabes?
Claro, así que se aprovecha luego del compilador.
Ya se fue.